I've had a number of you ask me about, well, how do we actually use any of this stuff? We've done a lot of definitions of things, but what does it look like when we get into design? And so the next couple of examples are intended to help you get a sense of that. Right? So we've got a structural member that has a centric axial load. That means it's going through the geometric centroid of the cross-section. When we pull on it, this is kind of like that wacky fun noodle, that flotation device for swimming pools, much stronger and stiffer, because we're going to pull on it with 100,000 pounds or 100 kips. Right? So very, very large force here. That RP is 100 kips. We got a round member, right? So, and as a constant cross section, we have a required factor of safety that is at minimum going to be 1.75. So the actual strength, we want it to be at least 75% greater than demand. That's with respect to yield. Okay, and where the material is A36 steel. Now, when you go look up A36 steel, you're going to find out that A36 steel has a yield stress value that we take for calculations to be 36 KSI, and that was intentionally chosen in that instance to be the same. It isn't always that way. This is an ASTM designation, and these numbers don't have to correspond to the yield stress, but it does in this instance. So if you have some other material, you just got to go look up what value do we tend to use. We'll talk later on in another instance about when you do the test and you get those values and it's not one number, how do you decide what number is going to be used? We are going to find the minimum diameter that's needed for this situation so that we have at least a factor of safety of 1.75. Right? We're going to do that based upon stress. So let's set this up here. The applied stress, and this would be axial, is going to be sigma equals P over A. So that would be then 100 kips divided by our cross-sectional area. And of course we know that A equals pi d squared over 4. So that'll be useful. And then we know what the criterion stress is. That's 36 KSI. So our factor of safety then we've got factor of safety is going to be our applied stress. Nope, it's not either. It's going to be the criterion. See, you got to think carefully about the criterion stress divided by the applied stress. That's going to be our yield stress divided by our applied stress. And our applied stress is P over A, so, that's interesting. And we want that to be greater than 1.75, that ratio. Right? So our strength over the demand is going to be greater than 1.75. Right? I hope you can see how we can go about getting what we want, because sigma applied is P over A, and A is pi d squared over 4. So that would be 100 kips times 4 over pi d squared. Right? And that would go into here. So we're going to solve for D, and we'll have then 36 KSI over our applied stress, which is now going to be 400 kips, and we got the pi d squared that's in the denominator of the denominator, so it comes all the way back up, pi d squared. That's got to be greater than 1.75, and then we take all that stuff to the other side. Let's see what happens. We get 1.75 times 400 divided by 36 divided by pi equals 6.189. Take the square root of that, and so D has to be greater than 2.49 inches. So in other words, we could use our D of 2.5 inches, and we should, in this instance, get what we want. Now let's just check that out. If we had 2.5, which is 1.25 for the radius, square it times pi, we have 4.91 square inches. And if we then divide that into our applied force, we get a 20.37 KSI axial stress. And if we then divide that into 36, our criterion stress, we get a factor of safety of 1.767. So that has worked out the way we intended. Right? So that's a design kind of scenario. Now this other one, we've got a W10, but let's do that next. Let's not do that right this second.